4.5, the Moivre's theorem. So this theorem will concern power of complex numbers. Power of complex numbers in trig form, because we already know how to do powers of complex numbers in a standard form. So here is the trig form of a complex number z with modulus r and argument theta. We already know that. So z squared would be z times z. So we multiply the modulus and we add theta plus theta will be 2 theta plus I sine 2 theta. Z to the third will be multiply z 3 times. And we see a pattern going on here. So we can summarize this. And that actually is the Moivre's theorem, that if z is equal to r cosine theta plus I sine theta, and n positive is an integer, meaning 2, 1, 2, 3, 4, 5, then z to the nth power is r to the n cosine n theta plus I sine n theta. This is a very quick and easy way to find powers of complex numbers as long as they're in the trig form. So example 1, use the Moivre's theorem to find -1 plus root 3i to 12th power. Now we see if we have to do this using the standard form, we need to FOIL this 12 times, not practical. Instead, let's write our number z, which is in a standard form given. Let's write it in trig form. So r, the modulus, is square root of -1 squared plus root 3 squared. We have a formula, and that's exactly square root of 4, which is 2. Now the theta will be the arctan, or inverse tan, of b over a. So it'll be root 3 over -1, which is inverse tangent of -root 3. So that is, the angle theta is 2 pi over 3. Now we can see that in the unit circle. Where is tangent negative? In the second and fourth quadrants, in the second quadrant, right here. That's 2 pi over 3. We know, here's what we know the tangent of pi over 3 is it pi over 3 here? Tangent of 60, yes. Tangent of pi over 3 is root 3, okay? So tangent of 2 pi over 3 will be negative. That's how we figure this out. So now we have r2, and we have the angle is 2 pi over 3. We can write a number z, which was given in the standard form. Now we can write that number in trig form. Okay, so the writing got a little behind, but it's catching up. So in trig form, r is 2, so cosine of the angle 2 pi over 3 plus I sine 2 pi over 3. And now that we have the number in trig form, things are easy. All we have to do is take it to the 12th power. In other words, n equals 12 in our formula. So that's going to be 2 to the power 12 cosine of 12 times 2 pi over 3 plus I sine 12 times 2 pi over 3. Simplify. So 2 to the 12 is 4096. Cosine of, so if we cross 12 and 3, that's 8 pi, plus I sine 8 pi. But 8 pi is the same, it's coterminal with 0, or 2 pi. So that's cosine of 0 plus I sine of 0. Now cosine of 0 is 1, sine of 0 is 0. So that's actually 4096. So we got a real number for the 12th power of our number z. All right, the next thing we're going to do is roots of complex numbers. Roots of complex numbers. So far we did multiplication, addition, powers of complex numbers. Now it's time for roots, which we have not done in standard form. So we have to do it in trig form. The fundamental theorem of algebra says the polynomial of degree n has n solutions. So let's write this down. The fundamental theorem of algebra, which we did early in this chapter, says that polynomial of degree n has n solutions in the complex number system in C. So x to the 6 equals 1. It's a equation of 6 degree, has 6 solutions. All right, let's see that. X to the 6 minus 1 equals, let's factor it, x to the third minus, oh, I can do that with another step here. I can write it as x to the third squared minus 1 squared, difference of two squares, x to the third minus 1, x to the third plus 1. And then continue to factor. This is a special formula as well. X minus 1, x squared plus x plus 1, x plus 1, x squared minus x plus 1. Now, we know that x is plus minus 1 from this factor here and this factor here. But the rest, we have to use quadratic formula. So x equal for the second factor, for this one, we're going to have x equals negative 1 plus minus square root of 1 minus 4, so negative 3, which is square root of 3i over 2. And for this one, quadratic formula again, so it's going to be 1 plus minus square root of 3i over 2. So how many do we have? Total of 6. So we have 6 solutions. 6 solutions, 2 real and 4 imaginary. Each solution is, or root, 6th root of 1. Because we started with the equation x to the 6 equals 1. So the solutions of this equation, they're going to be 6 roots. So let's write a formula now, or a definition. So definition for nth root of a complex number. Nth root of a complex number. So if I have some number u equals a plus bi, which is, this number is complex and is an nth root of complex number z. Okay, and that is if z is equal to u to the power n equals a plus bi to the power n. So we say u is the nth root of z. Finding the nth root of a complex number. Now that's important. How to find nth root of a complex number. N is positive integer. That means square root, cube root, and so on. Here's a number z written in the trig form. And this number has exactly n distinct, that means different, nth roots given by this formula. So we're going to have nth root of r, the modulus, and then cosine of the angle theta, which is our argument, plus 2 pi k over n plus I sine theta plus 2 pi k over n. So this is our formula for finding the nth root. and I'll explain it. It's a little long, but k is a new number he introduced, and if k equals 0, you get the first root, k equals 1 the second, and so on until n minus 1. So if you're finding sixth root, k is going to be 0, 1, 2, 3, 4, 5. So let's have an example of the same situation we had when we started with factoring in the beginning, but we're going to use this formula. So find all sixth roots of 1. Okay, so our example that we started here was x to the 6 equals 1 has 6 solutions or 6 roots. So it's the same problem, but we can have a different way of solving it. So number 1 is real, right? 1 is real, and we can write it as in a trig form. 1 is r, and the angle is 0. So here you go. 1, the real number 1 written in the trig form. So we want to find the sixth root. So the sixth root of 1, that's our formula, right? Nth root of r. I'm going to write here what we're doing. N is equal to 6, okay? If we're doing sixth root. And then cosine of 0 plus 2 pi k over 6 plus I sine 0 plus 2 pi k over 6, where k is equal to 0, 1, 2, 3, 4, and 5. So for each k, you get a root. Now, let's do substituting, but before that, I want to simplify. So what's sixth root of 1? That is 1. And then cosine of, ignore the 0, 2 over 6, pi k over 3, plus I sine pi k over 3. And we don't need that 1 on the front, right? So cosine pi k over 3 plus I sine pi k over 3. So now for different k, if k equals 0, if k equals 0, you're going to get the first one, which is cosine 0 plus I sine 0. Sine of 0 is 0, so that's equal to 1. So for k equals 0, you get 1. The first, it makes sense. The sixth root of 1 is 1. One of them. That's the real one. If k equals 1, you're going to have cosine of pi over 3 plus I sine pi over 3, which is equal to cosine 60 is 1/2 plus root 3 over 2 I. So this is another root. That's the second root. Then k equals 2, you're going to have cosine 2 pi over 3 plus I sine 2 pi over 3, which is negative 1/2 plus root 3 over 2 I. And so on. K equals 3, you have cosine of 3 pi over 3 plus I sine 3 pi over 3, cancel the 3, cosine of pi is negative 1. Okay, so sixth root of 1, here's another real one, is negative 1. K equals 4, cosine 4 pi over 3 plus I sine 4 pi over 3 equals negative 1/2 minus root 3 over 2 I. And finally, k equals 5. You have cosine of 5 pi over 3 plus I sine 5 pi over 3 equals to 1/2 minus root 3 over 2 I. Now, the interesting thing is that all these six roots are situated symmetrically in the unit circle. So here's the unit circle, and here's our first root, 1, or 1 plus 0i if you want to, 1 or 1 plus 0i if you want to write in standard form. Then we got, for what is the angle here? 60 degrees. For k equals 1, we got the angle 60 degrees. So that's somewhere over here. The second root is 1/2 plus root 3 over 2i. So this is the next one. And then we got, the next angle was 2 pi over 3, so negative 1/2 plus root 3 over 2i. And then we got negative 1, which is negative 1 plus 0i. And then we got 4 pi over 3 for that angle, negative 1/2 minus root 3 over 2i. And then we got 5 pi over 3 right here. And that is 1/2 minus root 3 over 2i. So these 6 roots are situated symmetrically with respect to the unit circle, okay? So this is 60 degrees. Between them, you have 60 degrees, okay? All right. So this is 60 over here, and this is 60, and this is 60, and this is 60. So all 6 of them are within 60 degrees from each other. And that's not an accident. We're going to see that happening a lot with the roots. So another example, example 2, find the 3 cube roots. Find the 3 cube roots of the number z equals negative 2 plus 2i. So a number z is in a standard form, but to use a formula for finding roots, we need to write it in the trig form. So what is r? R is square root of negative 2 squared plus 2 squared, which is square root of 8. I'll leave it like that. So we have square root of 8. And then what's the angle? We want to write this number in the trig form. So we want the angle. We can sketch a picture, or we can use the formula that theta, the angle, is arctan, or inverse tangent, arctan of b over a. So 2 over negative 2, which is arctan of negative 1. We know the angle is 135 degrees, so in the second quadrant. So back here, our trig form is cosine of 135 degree plus I sine 135. We can do degrees or radians, it doesn't matter. So here's our number in the trig form. So, oh, I didn't want to write it here. That was R. Okay. So I needed to continue writing the number over here, 135 plus I sine 135. This is the trig form right here. We're going to use this form to find, what do we have to find? The cube root. So to find the cube root, we do, I'm going to do this, cube root of z, and they're going to be 3 of them. So that is cube root of square root of 8, and then cosine of 135 plus, instead of 2 pi, I'm going to use 360 since we're doing degrees, 2 pi k or 360k over n, but n was 3, right? So if you want to find the, here n equals 3, if we have the cube root, plus I sine of 135 plus 360k over 3, so it's the same, equals cube root of square root is 6 root of 8. I can leave it like this, or simplify it, actually. I can do this. Yeah, let's do 6 root of, and instead of 8, that's 2 to the 3rd. How's that? And then cosine. How about we start k equals 0, 1, and 2. So if k equals 0, let's do this. Let's start for k equals 0 and simplify. For k equals 0, we're going to have 6 root of 8 and then cosine 135 over 3 plus I sine 135 over 3. Simplify that. 6 root of 8 is actually root 2. You can think about 8 is 2 to the 3rd, so that's square root of 2. And then cosine 135 over 3 is 45 plus I sine 45. We know those values. Cosine 45 is root 2 over 2 plus I root 2 over 2. Distribute root 2 times root 2, that would be 1 plus I. So this is our first cube root, 1 plus I. The second one, we'll find if k equals 1. So we're going to have 6 root of 8, again, cosine of, let's see, here's our formula right here. This is what we're looking at. So if k equals 1, we're going to have 135 plus 360 divided by 3. That will be 135 plus 360 divided by 3 plus I sine of the same thing. If you simplify, that was square root of 2 cosine. That ended up being 165, which is not an angle. We know the value, so you can use a calculator. And multiply by root 2, you get negative 1.3660 plus 0.3660I. So this is our second cube root. And finally, k equals 2. We're going to have the third one. So square root of root cosine of 135 plus k equals 2. So that would be 720 over 3 plus I sine 135 plus 720 over 3 equals to root 2 cosine 285 plus I sine 285 degrees. And approximately this is 0.3660 minus 1.3660I. If you sketch those roots on the unit circle, you'll see that they are again symmetrical around the circle. And this concludes this video.